Okay, good afternoon, everyone. So welcome to our distinguished ECE and ACME seminar. Today we are very honored to have Professor Onur Mutlu here joining our ASU's distinguished lecture series. And let me give you a brief introduction about Onur Mutlu himself. So Onur Mutlu is a professor of computer science at ETH Zurich. He's also currently a visiting professor at Stanford University and also a faculty member at CMU. His current broad research interests are in the computer architecture, system hardware security, and bioinformatics. A variety of his techniques, along with his group and collaborators, has invented over the years, have influenced the industry, and have been employed in commercial microprocessors and memory storage systems. So Professor Onur Mutlu obtained his PhD MS in ECE from University of Texas at Austin, and his bachelor's degree in computer engineering and psychology from University of Michigan. He also started the computer architecture group at Microsoft Research, and he had various industry position at Intel Corporation, AMD, VMware, and Google. So he also received a lot of rewards throughout his career, and he is ACM fellow, fellow, and also he's an elected member of the Academy of Europe. And I also want to note that Professor Onur Mutlu has taught the computer architecture, teach the logic courses throughout his career, and he is very generously, freely published his whole series of lectures freely on the YouTube. I'm sure some of you, if you are working in the computer architecture area, you already watched his videos. When I was a graduate student, I benefited a lot from them. So I really want to thank you on that. And with this, I think all the students cannot wait to hear your lecture.
Okay. Yeah, thank you very much. Yeah. Thank you very much, Jeff, for inviting me, and thanks for the generous introduction. It's great to have a full room over here. This is working, right? Okay, so I can get started. I'm going to talk about something that we've been working on for more than a decade or so, which I think is going to be much more important going into the future, which is memory-centric computing. A lot of this talk is going to be motivation. I'll give you a choice later on in the end, and I'll bias the choice a little bit in terms of what to discuss. But I definitely have a lot more slides than I can discuss within the course of 1 hour. So please feel free to ask questions in the middle or anywhere. We don't have to cover everything over here. There's a lot over here. In fact, I think I've used the same slide deck for 6-hour tutorials and some conferences also. So hopefully it'll be interesting. So I think it's clear today that computing today is bottlenecked by data. We're doing a lot of data processing, and important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And we want to do increasingly sophisticated things on more amounts of data, basically. We can generate much more data than we can process. I'll give you some examples over here. But an obvious example is machine learning, of course. I don't want to spend a lot of time on machine learning. Clearly, there are a lot of people working on it. But this is a nice talk that was given by the CTO of Cerebras, which is a company that's building chips that are this big, essentially wafer scale processors. And the goal, the reason they're building these chips that are this big is because of what they show over here. Memory requirements of models, AI models are growing, and compute requirements are growing, and they're both growing exponentially. And in the end, we're going to have a lot of trouble putting a lot of compute and memory at the same chip. And that's why they want to put a lot of compute and memory together in that wafer scale chip. So their approach is actually an example of near memory computation. We can go into more detail, but essentially their chip, I believe, has 80 gigabytes of SRAM today, which is not enough of what we have. Okay, this is just to give you an example. I'll give you some other examples. There are many, many traditional examples. It's not just machine learning. There's databases, graph processing, data center workloads, in-memory data analytics. Data is growing over here. And all of these workloads are bottlenecked by data in the end, performance, energy, but also reliability, security, et cetera, which we will briefly talk about. On the mobile end or edge end, there are also workloads that are really straining us because of the amounts of data that they process. And again, we're bottlenecked by data over here. I'm going to give you some numbers later on, and then we're going to talk about how to alleviate the problem. This is an area that I do a lot of work on, genomics. And this is an area where data is really exploding, even more so than machine learning, in my opinion. Basically, today, because of the technologies that people have developed to sequence genomes, we are able to sequence a lot more genomes at lower cost. So if you look at this picture over here from NIH, essentially, this shows the cost of sequencing genomes is reducing much faster than the cost of the transistors that we can put on a chip. And this means that basically the data is growing much faster than the number of transistors that we can put on a chip. This is a very fascinating area. Clearly, in the end, you can produce a lot of data, but processing of data is bottlenecked by whatever we can do in our systems today. And in the end, scientific discovery and adaptability to things like COVID, for example, is limited by data. I'm going through these relatively quickly, but these are motivation in the end. Clearly, genomics has a lot of applications. If you're interested in it, I'd be happy to talk about it, or you can read some of our introductory papers that talk about it. So this is one device. This is a data generator. If you look at this device, this is a nanopore sequencing device. You can get a lot of data. Actually, this was used in COVID-19 sequencing initially. A lot of these were sent to China initially when COVID-19 was discovered there. And it's been very useful. This is a great device for data generation. It's a terrible device for data analysis. So I think this device, this picture should give us some pause. Are we doing the right thing in our systems today? We're very good at generating data, but we cannot process the data. We have to move the data from this device far away, usually to a data center. So at the macro scale, we're causing a lot of data movement. Even at the micro scale, if you move this to a laptop, for example, the laptop, the operational principles of a laptop is actually not good for data analysis. And I'm going to talk about that. OK. So I think if you don't remember anything else from this talk, maybe this picture would be good to remember. Basically, we have very special purpose machines that are great at generating data. They're very fast at the data that they're generating. This is a genomics machine, another genomics machine. We have to move the data somewhere else to do the processing. And usually, that somewhere else consists of general purpose processors. Things are changing a little bit with accelerators, et cetera. But most of our infrastructure is still general purpose. There are two problems with it. Basically, we have general purpose processing capability that doesn't match the special purpose processing data generation capability. And the second problem is this huge data movement that happens at the macro scale as well as within the micro scale over here. We're going to talk a lot about the micro scale, which means how do you design these systems such that they can be specialized, and at the same time, they don't move the data as much internally. But don't ever forget about the macro scale, because we're moving data out of these big data generators to somewhere else. And that actually consumes energy and cost performance. Now, you can replace a special purpose machine with a video camera. You'll have the same picture, basically. You can replace it with web clicks, and you'll have the same picture. We're great at generating data today. OK, so if you're interested in genomics, you can read more of our papers. I'd be happy to talk about it, as I said. So essentially, today, data is overwhelming our machines. It's overwhelming the storage capability, communication capability, and in the end, computation capability. We actually designed great machines for computation today, but they're being bottlenecked. They cannot really exercise their computation capabilities. So if you go back to the fundamentals, a computing system needs to have computation, communication, and storage and memory. And if you look at the history of computing, we focused a lot on the computing units. I would say disproportionately so. The rest is kind of ignored. You can see this in industry also. The industry is very much focused on computing. We don't talk as much about memory. Everything else over here that's other than computing is not doing computing, essentially. That's the reason. OK, so let me give you some real pictures. This is not my real picture. This is actually my cartoonish picture. This is from my first NSF proposal when I was at CMU. And the picture is still somewhat the same. Basically, what you see over here is a general purpose processor. It has some cores or accelerators or heterogeneous cores, whatever. Essentially, other than these cores, everything else is dedicated for storing and moving data. Caches, interconnects, other interconnects, memory controllers, other interconnects, other caches, other interconnects, and storage. So if you do the analysis, more than 95% of a single node today is dedicated to moving and storing data. And if you look at the core, most of it is memory also, actually. There's SRAM and register files, right? So if you give this picture to a 10-year-old and say, oh, I'm dedicating all my resources, almost all my resources to storage and memory, they would say, oh, OK, great. Then you should not have any data bottleneck, right? Yet our systems are still bottlenecked by data today. So I think maybe we should be like 10 years old and thinking about our systems from a scratch, like blank slate. OK, so you don't like my picture. This is AMD, a real chip. And you can see that that green box is L2 and L3 caches. And there's a global memory interconnect over here. There's PCI Express, et cetera. So most of the memory chip is basically data, communication, and storage. And we're adding more. It's actually beautiful technology. It's 3D stacking, and they add more caches on top of it. So the question is, at what cost? So this talk is going to be about at what cost, basically. We're having this beautiful technology to do compute, but are we really doing the right thing in our systems? OK, if you don't like AMD, this is IBM. Again, the same picture over here. I could keep going on. But if you look at, actually, this is fascinating to look at. I will derail a little bit. But most of the chip is actually, this area over here is all about data communication, right? We've solved the computation problem. I will argue that computation is not a bottleneck anymore. It's really all about the data movement in the system. OK, so maybe I'll give one more picture over here. This is a full SoC, full system. So if you look at one of the most state-of-the-art systems, you have multiple chips over here, chiplets. You connect them somehow. It's a lot of SRAM in the end, a lot of interconnect. And there's this darkness, DRAM. And there's an even bigger darkness over here, which is storage. And most of the data is actually there. And then there's sensors. OK, so let me give you some numbers. We've done a lot of analyses on this data movement issue and data issue. These are some workloads that we examined during my last sabbatical at Google. And we found out that more than 60% of the total system energy in those workloads is spent on data movement. And this is not even an average use case. This is actually not so intensive workloads. That number increases significantly. We also did more work with Google and analyzed their edge machine learning models. And on a state-of-the-art machine learning accelerator, the HTPU, we basically showed that more than 90% of the total system energy is spent on memory. OK, so my axiom going forward in this talk is that we want to design intelligent architectures because these architectures are actually going to be making decisions for us. That's what the big ML AI hype is all about, right? They're going to be helping us in many dimensions. But fundamentally, the architecture also needs to be intelligent to help us. So, and for that, I think the architecture needs to handle data well. So what does it mean to handle data well? There are three directions that we're following. I'm not going to talk about the second and third one because we don't have time. I'm going to focus a lot on the first one. We should ensure that data essentially doesn't overwhelm the components that we design today. And this leads us to intelligent algorithms, architectures, and system designs, essentially co-design across the stack. The second part is we should use data for our benefit because there's a lot of data and metadata flowing through the system. If we could use that so that we can actually improve the system level decisions that we're making, for example, use machine learning in our controllers, memory controllers, for example, that actually enables a lot of possibilities. I don't have time to talk about this, but we call this a data-driven architectures. And the third one is, even though there's a lot of data that's being processed in the system today, and data has a lot of properties. If you think about data, it has performance properties, security properties, privacy properties, approximability properties, fault tolerance properties, and you can keep adding these properties. These properties don't get communicated to the underlying architecture in most systems. If you actually communicate that information to the lower levels, you can make much more intelligent decisions because you distinguish different data with different properties. Again, I don't have time to talk about this, but we call these three different directions, essentially data-centric, data-driven, and data-aware directions. This talk is going to be about the data-centric direction. OK. So in the end, I think we need to revisit the entire stack in all of these directions, because if you think about the stack we built to express problems such that the problems can be solved by electrons in the end, this stack doesn't take into account a lot of that. It's very processor-centric, as we will discuss. OK. So let's jump into this data-centric component. Again, feel free to interrupt me if there are questions. Even data-centric component is very interesting because when I think about like what should be the data-centric architecture, you can come up with multiple things, right? We're going to talk a lot about processing data where it resides or where it makes sense. But I think we also need to rethink how we actually design our system. So if data is really important, how should we really access it? I think low latency and low energy data access is going to be a lot more important. There needs to be much more research over here. Low cost data storage and processing is important, and intelligent data management. I'm going to talk about this also, because I think we're having difficulties in our designs today, especially with technology scale. But most of this talk is going to be about processing data where it resides. Okay, let's talk about this. So I call processing data where it makes sense. And there are a lot of places where it makes sense. Essentially, data gets input from sensors, and it gets stored in storage, DRAM, SRAM, et cetera. Today, we're actually processing only in the processor, and very small parts of the processor. Why don't we process everywhere, essentially? Then the question is, of course, what should be processed where, right? Sometimes it makes sense to process the data in the processor because you have a lot of good locality. But in many times, it doesn't actually. So in the end, our goal is to distribute the processing across the entire system. Okay, this is not a new idea. We should really acknowledge when these things have started. These are the oldest papers that I could find. This is a beautiful paper that calls, essentially, this is a near memory processing idea. They called it logic in memory. I would recommend people to take a look at it. And Harold Stone, who did a lot of work in this area, he has a beautiful textbook on computer architecture, also high performance computer architecture, an old one right now. But he also worked on logic in memory computers. So what has changed today? And people have actually worked on this for a long time since these ideas were initially started. I think today the environment is a little bit different, and we also need to be thinking differently. Basically, for a long time, we didn't have a lot of problems with memory technology. Today, we're having a lot of problems with technology at the lower level of that stack. And we're also having a lot of problems at the higher level with the scaling of applications and systems because they're bottlenecked by data. Right? I'm going to talk about both of these. I'll quickly talk about the technology problems. Basically, memory technology scaling is not going well. I'm going to very briefly talk about RowHammer problem. That's one of the examples of problems. And there are many scaling issues that demand much more intelligent memory controls. And this is already happening in industry. And it's good to see that this is happening in industry. On the application and system side, we're having data access bottlenecks, energy and power bottlenecks, and data moment energy dominating computation energy. And on top of this, we're greedy as humans, right? We need performance, energy, and sustainability all at the same time today. If you want to improve all of those metrics, you need to actually think about a different model of computation. I think minimizing data moment is required. So basically today, as opposed to, let's say, 1970s, 80s, or even 2000s or 2010s almost, we're kind of getting squeezed in the middle. The paradigms with which we're building our systems is actually not working very well. That's why we're seeing the energy results that I showed you earlier. Okay, let's jump into this a little bit more. Like before I jump in, basically I should say that if I was giving this talk in 2019 or even 20, you wouldn't see the slide. You would see this hybrid memory cube. Basically today we have interesting technology and people are experimenting with it. You can have 3D stacking technologies where you can put computation in the logic layer and the memory layers would be on top of that. If we have time, we'll talk about that. People have been experimenting with processing inside DRAM. And more recently, this is UpMem company. We did a lot of work together with them and also using their systems. They put actually processing inside the DRAM chips. So people are actually doing these processors. Samsung has introduced their DRAM chips with processing capability inside them. So did SK Hynix. And there are also other efforts like putting chips on the memory modules so that you can do processing for recommendation systems for machine learning. And even companies like Alibaba have produced their own DRAM chip prototypes where they can do processing. So this is good news, basically. I gave a lot of versions of this talk before 2021. Now I'm happy to see that industry is actually doing a lot of these things in a good way. And there's more coming. Clearly, this picture doesn't cover everything. There are many other experimental chips and startups that are trying to do more data-centric computing. Okay, there's some examples. These are more recent examples where the communication interfaces of chip, the compute express link interfaces enabling offloading computation to the memory side, essentially. You can read papers also. Okay, so we've been arguing something like this for a long time. This is a paper that we wrote to International Memory Workshop, an invited paper, where we argued that memory scaling issues are going to get worse. And if you want to solve these technology scaling issues, we should not think of memory as memory, but memory as part of the bigger system. So if you want to scale memory, you should really think about memory system co-design. And I think that's what data-centric computing is about. Now, let me give you the example of the technology scaling. Basically, as memory technology scales, we start having a lot of issues at the lower level. Scaling means that you're reducing the size of the circuit, so it becomes much more vulnerable to different types of noise effects. And those noise effects manifest itself as reliability problems and robustness problems in general. So one of the things that we have found is that you can predictably induce errors in DRAM memory. And this is actually a phenomenon that's widespread in essentially all DRAM memory chips. This is known as the RowHammer problem. How many people know about the RowHammer problem? Okay, how many people do not know about the RowHammer problem? Okay, that's good. Don't be shy. So this is a problem basically. If you have DRAM chips, which is essentially all of the main memory today, you can induce bit flips in those DRAM chips. So what's the problem? I'll give you the specific example, but there are many other examples that are coming up down the road, I would argue. Essentially, memory consists of rows of cells. If you want to access a bit in one of these rows, you need to activate that row, meaning you apply high voltage to that word line. Now, if you want to access something else in some other row, you close this row, deactivate this row, or apply low voltage to that word line. Now, if you keep doing this repeatedly, activate precharge, activate precharge, activate precharge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, it turns out cells, vulnerable cells in physically adjacent rows flip, meaning they lose their charge over time. I'm not going to go into the mechanics. This is not a RowHammer talk, but this happens in real chips. And we've demonstrated that it essentially happens in all chips unless you have a mitigation mechanism for it. So why is this happening? Because there's not enough electrical isolation. Cells are too small and cells are too close to each other. They're affecting each other. And we call this the hammer drop, and we call these the victim rows. And we showed initially in our original paper, more than 80% of the chips that we tested are vulnerable, but actually you can put that number to 100%. Later papers show that it's 100% essentially. And what is worse is clearly this is a data corruption problem. It could happen in benign applications, but it could also be used by a malicious attacker as a security problem. Someone can actually induce those bit flips to take over your computer. And there are many papers that have shown that later on. Again, I'm not going to talk about these in detail. You can read our original paper and also later papers that we have written. There's still more going on in this area. This is not a solved problem yet. Why am I telling you all of this? So clearly, I was supposed to talk about data-centric computing, but one of the motivators of actually doing processing near memory is building intelligent control so that we don't run into issues like this. And this is actually, I believe, necessary. Again, I will not give you the whole history, but more recently, finally, the industry has written papers about their own intelligent controllers to solve the problem. This is a paper from SK Hynix in ISSCC 2023, major circuits conference. They finally wrote a paper acknowledging the problem. And they basically said that they put intelligent controls essentially into the DRAM chip. You could argue how intelligent it is, but it's much more intelligent than what a DRAM chip is today. Basically, they modified the DRAM chip significantly enough to add counters to each row. And whenever each row is activated, you increment the count. And internally, they take some mitigating action, like a refresh, for example. If the counter is if a row is activated too many times, they refresh adjacent rows so that the data is not corrupted. I'm not saying that this is the best solution to the problem. In fact, I have a lot of qualms with it. But it is a solution that has some intelligence inside the DRAM chip, which if you actually went to SK Hynix 10 years ago and asked them to implement something like this, they would kick you out of the door. Because this actually cuts into their costs significantly. But they're now adding these intelligent controllers to solve this problem. And this is good because this is computation inside memory. If you think about this, you're doing computation, right? You're counting accesses. You're taking some mitigative actions. This is slight intelligence, right? So I think this is a step in the right direction. And of course, other companies have to write papers after seeing SK Hynix's paper, but like Samsung. This is a very hard to read paper, so I wouldn't recommend implementing the solution. And I think it has some issues also, but take a look. Okay, so basically, the reason I'm telling you all of these technological issues is we need intelligent controllers. And these are not going to go away. This is a paper that we presented at ISCA that shows that these problems are going to get even worse. Essentially, this is the row press vulnerability. I'm not going to go into it, but basically, this paper shows that you don't need to have many activations to induce a bit flip. You can actually activate a row only once, and you get a bit flip. Of course, this requires violating the timing parameters, but this shows the extent of the problem. So the solutions are not going to be easy, but those solutions are going to be important. Okay, if you want to read more. So some of you may say, okay, these are DRAM old, clearly old technology, right? And you may say, actually, oh, there are new technologies that should be investigated, and I absolutely agree. We should really be looking at all kinds of technologies. Unfortunately, we don't have a perfect memory technology. We've been actually doing a lot of work on emerging technologies for a while as well, including phase change memory. Unfortunately, none of these technologies have perfect reliability. And as they scale to the sizes at which we're manufacturing DRAM or flash memory today, they're going to have even more problems. So you really need intelligent controllers and emerging memory technologies also, unless you answer the like $1 trillion question of finding the perfect memory that's good at everything, which is going to be tough. Okay, so basically, this is the technological motivation for more near memory computing. Essentially, we need intelligent memory controllers to avoid these failures and enable better scaling. Feel free to ask questions. This is a good point to ask questions if you have one. Otherwise, I'll keep going. Yes?
Side or on the host side?
So that's a good question. I'm talking about intelligent controllers everywhere. Yeah, it could be, if it makes sense to have it in the DRAM side, it makes sense. And in some cases, it makes sense. But it could be on the memory controller side also. Yeah.
Do you think like by like reduced cost integration would be better to have on the memory controller side? Lower, you know.
Potentially. Depends on, I mean, there, I think both research as well as industry constraints come into play. But there are advantages to having things in the memory controller. You could modify things more easily also. But I also believe in doing the right things at the right place. So there are some things that you can do in DRAM with the knowledge with which you're manufacturing DRAM that you cannot do on the memory controller side because you're not manufacturing DRAM. For example, if you know the characteristics of your cell much better, a solution on the DRAM side might be much easier. Yeah. Okay, I'd be happy to talk about that, but we have a paper that talks about that on self-managing DRAM. Okay. Yes.
Logic and memory.
Yes.
Make the problem of reliability of that memory far worse.
So that's a great question. Certainly, that logic also needs to be reliable, right? And yes, it introduces a little bit more challenge, but it may actually solve some of the challenges also. Yes, it needs to be considered, no question about that.
All the elements and all the package that logic comes with.
Yeah.
Now combining that with your memory.
That's true, yes, yes. So there needs to be more protection. I agree, but I think my even maybe longer term comment on that is, we've been used to designing memory as memory. We should really be thinking memory as a computation engine. And once you start thinking of memory as a computation engine, everything we do in computation engines today should be ported to the memory side as well. Except we don't know how to do it perfectly yet. Yeah. Okay, let me give you the higher level view, system and application. I've already said a lot of this, but basically we're having a lot of issues with data access energy and data movement energy today. In my opinion, actually, there's an even bigger issue. Basically, we're consuming a lot of energy in our systems. I gave you the energy numbers, right? Do we want a world that looks like this, or do we want a world that looks like this? Now, I would argue that we want the best of both worlds. So humans are greedy. We want high performance, energy efficiency, and sustainability all at the same time. We're way past the point where we say, oh, I want 5% performance, but it comes at 3% energy cost. I want 5% performance at 5% lower energy, if you like that 5%. Okay, so the problem is we're designing our systems completely with the wrong paradigm today, in my opinion. Basically, our current design principles require a lot of data movement. This causes great energy waste. This also causes great performance loss because we have a lot of latency in data movement, right? And to overcome that latency, we make our systems more complex, right? We add lots of mechanisms. We add heavy out-of-order execution, heavy prefetching. I showed you 95% of the system is about memory and storage. It's all cache hierarchies, right? We're adding more caches. When these work, they sometimes work. When these don't work, they actually waste a lot more energy. So we're actually in a vicious cycle right now. We're wasting a lot of energy because of data movement, and we're wasting a lot of energy by complicating our system to overcome the performance problems of that data movement. So how do you break this vicious cycle? Usually vicious cycles are broken by identifying the fundamental root cause. And I think in this case, we're doing processing far away from the data. Okay, I've already said a lot of this. Essentially, all data is processed at the processor. Expand that processor to the accelerator, FPGA, GPU, whatever you want, at great system cost. Now, let me give you some history over here very quickly, because I like some of this history over here. So how many people know about alpha architecture? Okay, everybody is showing their age over here. Old professors. How many people know about Dick Seitz? Probably the people who know about alpha. So Dick Seitz was a chief architect of the alpha processor in 1990s. They were actually built some of the fastest processors of their times. And after they built one of the flagship processors, he wrote this one-page article saying it's the memory stupid. He played with the election thing in the US at that time. Like some candidate was running saying it's the economy stupid. It's all about the economy, right? And this person was saying it's all about the memory. Basically, he said that we built this processor. It's the fastest of its time. It is able to finish 4 instructions every clock cycle. Unfortunately, on this important database workload that they think they built the processor for, it's finishing one instructions every 4.7 clock cycles. So it's operating at 5% or less than 5% of its peak bandwidth. Why? It's basically waiting data from memory. So that's 10 years. That's in 1990s. My PhD thesis was all about processor-centric approaches for tolerating those memory latencies. And we showed essentially the same thing with Intel's workloads. Most of the time, a state-of-the-art Intel processor is waiting for memory. Now, if you don't believe the sites, you don't believe me, fine. Everybody believes Google. So Google showed essentially the same thing in 2015. Again, a state-of-the-art processor, Intel Skylake at the time. Most of the time, their workloads are waiting for memory. You can see that the green part is when you're actually finishing instructions, which is what the processor is designed to do, finish instructions, right? Most of the time, it's not finishing instructions. Why? It's waiting for data. OK, that was the performance issue. So clearly, performance is important, and we're wasting our resources by waiting on data. Energy is even worse. There are a lot of data that you can look at, but this is a slide I like from Bill Daly. You can argue with all of these numbers today, but the relatives remain. So this is, at the time, a 64-bit double precision floating operation, 20 picojoules only. A DRAM read or write 16 nanojoules. That's 800x difference. So OK, today you can optimize it to maybe 100x, essentially. Essentially, a memory access costs 2 to 3 orders of magnitude energy than a complicated arithmetic operation. Now, this is interesting because this shows multiple things. One is we've been very successful in optimizing computation and logic. So Moore's law has worked really well for us. But we did not optimize the interconnect and memory very well. And the second is, if you actually want to do computation, does it really make sense from an energy perspective to bring data elements into the processor? Right? We're wasting a lot of energy, essentially. And if you actually do the calculations for locality, you need to reuse those data elements thousands of times to overcome this differential. OK, so that was a complicated arithmetic operation. What about a simpler one, a 32-bit? Today, actually, in machine learning, for example, people want to do 4-bit operations, 8-bit operations that are much simpler. A 32-bit operation, if you compare it to a memory access, the energy differential is 6400x. And this is DRAM. If you go to storage, multiply that by another 10x. So it becomes a little bit crazy, if you will, right? Why do we actually move anything from storage? Why don't we actually do all of the computation inside the storage device, which is actually a computing system by itself? So we need to be thinking outside the processor, I would say. OK, so that's why we see these numbers. More than 60% of the energy is spent on data movement, and more than 90% of energy is spent on memory in large machine learning models. OK, basically, I've given you all this motivation to say that we do not want to move data. We want to keep data where it is, and enable computation with minimal data movement, compute where it makes sense, where data resides. If it makes sense to do the processing in the processor by moving the data, do it in the processor, but only if it really makes sense. And how do you decide whether it makes sense? It's all about the equations, basically, performance and energy equations. So, and we need to create an ecosystem to actually understand, we don't have this yet, in my opinion, where to do the computation. So that's what data-centric computing is all about, in my opinion. Now I'm going to go into a little bit more detail, but I'll take questions before that. So the general idea is we want to keep the data where it is and store. Clearly, today, memory is, we store a lot of data in memory and storage. And the processor will ask memory, can you do this function for me on this particular data? And memory and storage will provide the results. There are a lot of questions over here. How do you design the memory and the controllers? How do you design the processors and communication units? How do you design the software and hardware interface to enable that? We don't have a lot of these completely yet. How do you design the system software compilers and languages to enable this? And I think this is also very interesting. If there may be those of you who are more algorithmically and theoretically oriented, how do we think the algorithms and theoretical foundations to actually take this into account? I'm going to talk about that theory a little bit. Basically, it's an across the stack problem. There's some devices, and then also there's, of course, question of how do these devices operate over here to do the computation. We'll talk about one particular way of doing that. And how do you match the algorithms to do that sort of computation? If you think about this, today, the theory of computing is very processor-centric. The way we, if you've taken, how many people here have taken a computational complexity course, algorithmic complexity course? OK, I see some hands. And what have you done in that course? You've counted operations, right? Big O notation, for example, big theta notation. The complexity of an algorithm is determined by the number of operations associated with it in an order basis, right? Well, what I've shown you earlier is that maybe that doesn't matter as much, right? Maybe data moment matters. Do we have a theory for data-centric computing, data moment? I think this is a challenge that I will have for people who are more theoretically oriented. How do you actually build a theory of more data-centric computing? And we don't even have that yet. This shows that how intrinsic this processor-centric approach has been in our outlook for the entire computing. Okay, so basically we need to rethink how we design computers. We have a lot of other processing and memory courses that I'm going to mention over here. But now I'm going to give you a little bit more on how we can do computing. First, I'm going to define some terminology, but since we don't have time to cover everything, I'm going to give you a choice. So in my opinion, there are two major approaches to data-centric computation. One is relatively similar to today's approach, except you get closer and closer to data. So you have the processor today here and memory here. They're far away from each other. The idea is to design the logic as we design logic today, but get it closer and closer and closer and closer to memory. This is processing near memory. Processing and memory technologies are distinct from each other, but they get coupled using either better integration or better technologies like 3D stacking. That's more traditional approach, which I wouldn't recommend you choose right now, at least. The other approach is you have the processor here, and then you have memory here. Forget about the processor. This is a memory device. But it's not just a memory device. Think about that memory device as a computational device also. Any memory device has some fundamental analog operational characteristics that can enable it to do computation and use that for computation. This way, you don't design the logic separately, and also you don't move the data as much. So that I call processing using memory. Now, which one do you want to talk about? Processing using memory, which is longer term, much harder, in my opinion, or processing near memory, which is already happening, in my opinion, in industry. Okay, who votes for processing using memory? Okay, I biased the coin maybe. Who votes for processing near memory? Don't be shy. Processing near memory has its benefits, and there's also a lot of interesting things, but you lost, sorry. So I'm going to talk about processing using memory. Okay, there's actually a bigger PIM taxonomy that I'm not going to go through because there's a nature of computation that I mentioned. There's a technology that you employ. There's a location. And processing in memory is really a tuple of these things, which I'm not going to talk about right now. But in the end, what I'm going to talk about is going to be memory as an accelerator. So there's a more fundamental paradigm over here, if you think about it. What I've been talking about is really every component is intelligent, and it can be its own agent. They all do computation. They can be equal agents. In the end, you have a distributed system. I'm not going to talk about that. I'm going to talk about still accelerating computation from the CPU side to the memory side. So memory will be an accelerator in the end. And we know how to build accelerators, except they've been sitting on the wrong side of the processor bus or left side of the processor bus. Why don't we build some, or memory bus, sorry. Why don't we build some accelerators on the memory side, essentially? Okay, I'm going to talk about processing using DRAM. This is just a one-slide quick summary. Essentially, we can support a lot of things in DRAM. I'm going to limit myself to DRAM, but a lot of the ideas are applicable to flash and also emerging memory technologies like RRAM, STT-RAM, et cetera. And also some other technologies can do even more operations that I'm not going to talk about over here. So in DRAM, what can you do? You can do bulk bitwise and or not and majority operations. You can do copying and initialization. You can do random number generation, physical unclonable functions, and you can do more complex computation using lookup tables at low cost. And the idea is to use analog computation capability. I'm going to give you some examples over here. Any questions so far? Otherwise, I'm going to give you some examples of how we do this. Yes, please. Okay, why isn't that simple? Because not a lot of workloads benefit from larger caches. So if you look at, for example, graph processing, there's not enough locality in graph processing. And so caches, of course, help, but they don't help everything. So you still go off chip to memory a lot of times. So those pictures, for example, that I showed you that show the processors are waiting for memory is because caches are not effective. Yeah. And people have built prefetchers to prefetch the data, and they're also not effective. And people have built multi-threading so that you can actually tolerate the accesses, but it's also not effective enough. And all of these increase costs significantly. Okay. Okay, I'm going to start simple. I'm going to start by cheating. But I think this cheating is important because we do a lot of copying and initialization in our systems. So if you look at many applications, they do a lot of copying. If you, for example, if you're initializing a 10 terabyte database, you write a lot of zeros to memory. And this takes a lot of time, not just initialization. So Google, in their paper that I mentioned earlier, showed that just these two function calls, memmove and memcopy, occupies 5% of their execution cycles in their entire data center. I think this is a huge number just for two function calls. And that's just part of the copy. So how do we do copying today? Basically, if you want to copy this white page to this gray page, 4 kilobytes, let's say, simple, not huge. Today, we go through the processor. Because memory has no intelligence, we cannot do this inside the memory. So we basically go through this memory bus to read this page byte by byte all the way into the processor, and then write the data back to this other page byte by byte. Clearly, this causes a lot of latency, energy, etc. And if you show this picture, I think we should be taking a more blank slate. If you show this picture to a 10-year-old and ask, is this a good way of doing things? Probably they will tell you, no, why don't you just go through here, right? I think we should be thinking in our systems as 10-year-olds going into the future. So how do we do that, basically? In-memory copy basically says do this internally. Now, how do you do that? I'm going to go through the benefits quickly, right? Low latency, low bandwidth utilization on memory bus, no unwanted data movement. Today, a 4 kilobyte page copy takes about 1,000 nanoseconds and 3.6 microjoules. We have a way of doing that at 90 nanoseconds and 0.04 microjoules if you do it internally. And internally, it's relatively easy, actually. If you know the structure of DRAM, you can do in DRAM copy. I showed you these rows before in a different context. You have a bunch of rows. If you want to copy data in one row to another row, what you do is you first activate the source row, which brings the data into the sense amplifiers, which are actually SRAM kind of structures that are strong. And then if you activate the destination row while deactivating the source row, the sense amplifiers get connected to the destination row and copy the data that they captured from the previous activation. That's the idea. By doing two back-to-back activations, you can do a full row copy within DRAM without moving the data outside the chip, without moving the data outside the subarray, actually. If you know the structure of DRAM, this is actually quite dense. I don't know how to make it faster. If you find a way of making it faster without modifying circuitry as much, I'd love to hear about it. But basically, it's two consecutive activates. And if you want to do it reliably, it's negligible hardware cost. And this gives you significant performance energy improvements. Of course, you need to provide mechanisms for moving the data between different banks, between different subarrays, et cetera. I'm not going to talk about that, but all of these numbers have improved with research over time. Hardware cost is really figuring out whether so to make it reliable, you need to really figure out whether the rows are in the same subarray or not. Actually, there's no real hardware cost if you want to do it without doing it reliable. I'm going to talk about that next very quickly. But basically, we published this paper in 2013. And these good folks from Princeton showed that using some of the infrastructure that we developed, you can actually violate the timing parameters in DRAM. And you can actually do this row clone operation in existing DRAM chips, which are not designed for this purpose clearly, by violating the timing parameters quite reliably. I think this is fascinating. DRAM is not designed for this, but we can actually do it in real DRAM chips. And we replicated their results and open sourced an FPGA-based infrastructure where we could actually tie this. So in the application, you can do a page copy. And what we do is in this system, that page copy gets sent to this FPGA board, which has a processor. And we actually ship the page copy to the memory controller and violate the timing parameters and do the page copy and get the results back to the application. So you can actually do an end-to-end evaluation with this system. Yes?
You talk about violating timing parameters.
Yeah.
Does it not have any effect on the system?
Yeah, like reliability? Technically, it could potentially have effects, but in reality, we don't observe those as much because here we're violating a particular timing parameter, which is the activate to activate timing parameter between two rows to the same subarray. If you know all of that information, almost all the time you get reliable. There are some other timing parameters if you violate, you may actually run into issues. Okay. If you're interested, we'd be happy to talk. So clearly, I'm not suggesting that we should be violating timing parameters. This shows just the computational capability of existing DRAM chips. Existing DRAM chips are not designed for this purpose, but even without that, we show that you can actually do this. Right? So you can actually improve initialization and page copy performance significantly. And if you're interested, you can actually use this, and we'd be happy to help. This PyDRAM infrastructure is all online. OK, so I cheated, as I said. There's more over here. So how do you do computation in DRAM? Again, some of this is doable in existing DRAM chips. we want to use analog computation capability of DRAM. And if you activate multiple rows, this actually performs computation. This was initially reported in a computer architecture letters paper, and then we had a micro paper after that. Before I go into the details of this a little bit more, I should say that new memory technologies are also capable of doing this. Flash memory is also capable of doing this, actually. In real flash shift, we demonstrated that even more reliably than DRAM. But some other technologies like memristors, resistor RAM, et cetera, they can do even more operations. Because of their crossbar array structure, you can do matrix vector multiplication in the analog domain. I'm not going to go into that. There's a lot of work on this topic, but it's good to examine many technologies. Now let me go back to DRAM and let me talk about how you do it in DRAM. So conceptually, if you have 3 different rows, A, B, C, I'm depicting only 1 cell per row, but imagine that you have 8 kilobyte row. And imagine that you have 1,000 subarrays. You can actually do whatever I'm going to describe in 8 million bits concurrently, limited by your memory capacity and power considerations. The idea is activate these 3 rows concurrently. Now, if you activate these 3 rows concurrently, they would be connected to the same bit line. And if at least 2 of these cells are charged, you get the charge state at the end in the capacitor. If at least 2 of these cells are discharged, you get the discharge state at the end because of charge sharing principles, right? So if you think about this, the majority function, right? If at least 2 of these cells are charged, you get the charge state. Otherwise, you get the discharge state. This is a bitwise majority. So this is computation. And this computation done in the analog domain, converted to digital using the sense amplifier over here. So we have a beautiful sense amplifier that's an analog to digital converter here. So it could be relatively reliable. I'm not talking about the variation effects over here. That's something we can discuss. So you can express C, and you set C to 1, you get the OR of A and B. You get C to 0, you get the AND of A and B. So now we have a bitwise OR, bitwise AND, and bitwise majority function. What's missing? What's missing is NOT. It's actually not missing. It's right here. If you activate 1 row or 1 cell over here, you get the complement of it over here. The key is how do you actually get it back inside there. So we have some mechanisms for that. I'm not going to go into detail. Yes. Yes. Yeah. Yes.
You have to now change the
yeah. Yeah. So internally, so this doesn't impact the refresh mechanism that much. Internally, actually, DRAM manufacturers do refresh in multiple rows. So they don't actually read 1 row at a time. They do actually multiple rows concurrently. There are some internal mechanisms. But this could, that refresh is initiated by the memory controller. And these operations are also initiated by the memory controller. So as long as you're not initiating these operations, as long as you're obeying the refresh timing parameters, you should not be messing with the refresh and retention times. Yeah. Yes.
Does it also not require to modify the row decoder to activate?
Yes. So all of these questions, I'll defer you to the paper. We're not suggesting that you should do this in every row in DRAM. We have a special area in the DRAM subarray where you move the data first and do the activation, do the triple row activation. This is what we call triple row activation, only in that special row area. That way you can get a very low cost row decoder. But that's a very good question too. Yeah. So there are a lot of practical issues that you can solve by slightly modifying the DRAM microarchitecture. Okay. So this is nice right now. So I didn't talk about NOT, but you can actually do the NOT also with some cost. I'm going to tell you a little bit more about something else soon. Now the question is, this is actually a very general purpose circuitry, right? You can do, it's essentially Boolean complete. And you can actually map your algorithm. You just need to think differently about your algorithms. Basically, you have a substrate that can do massively parallel bulk bitwise computation. What matches it? And initially, what matches it is where people are thinking about bitmaps, for example. So a lot of databases use bitmaps. Some databases are actually designed to operate on many, many bits in parallel. The bit weaving database, for example. Microsoft has designed a web search engine that operates on bitwise operations. And there are a lot of other algorithms that actually use bitwise operations. And I believe many things actually can be, many algorithms can be rethought so that they can use these bulk bitwise operations. I'm going to give you the database example. We actually ported the database, bit weaving database that was developed at the University of Wisconsin. We see significant performance, energy efficiency improvements in the original paper. So that's promising. So that was 2017. We wrote papers about it. More recently, we've been looking at how to make this more programmable and even more general purpose. This is a paper that we published in ASPLOS in 2021. The idea is actually relatively simple, I should say. We wanted to have a framework where the programmer can input an operation, And this operation can be specified as a logic circuit, for example. It could be a convolution, for example. It could be a matrix multiplication. You just specify it as a logic circuit. And we basically convert it to a majority inverter graph. And then we optimize it using design automation tools that were developed by Nani Demicheli's group at EPFL for quantum computing, actually. And then convert those to triple row activation and row clone operations in DRAM. There's some register allocation or row allocation also that we do over here. So you can actually automate this process. And in the end, you associate that desired operation, maybe a convolution, for example, with a microprogram that's in your memory controller. And this is your new instruction. And the programmer or the compiler inserts these new instructions. And when the processor sees those new instructions, it basically ships the instruction to the memory controller that's executed using that microprogram. So this is a very general purpose computing paradigm because anything can be computed over here. Of course, the efficiency of it is a different question, right? So this substrate is very good at bitwise operations, bit serial operations. It's not good at 64-bit multiplication, for example. It's not going to work very well. In fact, we analyze in the paper that as you increase the bit width, you're not going to get very good scalability. But all of the trends are actually for lower bit computation, right? Especially in machine learning today. Okay, so we show good results in the paper. You can read about those. It actually does quite well compared to high-end CPUs and GPUs. More in the paper. More recently, so there are issues with this because now you're doing bulk bitwise operations and we did not completely automate it. This was a paper that we published at HPCA last month that essentially shows that you could actually do this at smaller granularities as well. You don't always want to operate at 8 kilobyte granularity or 8 million bit granularity, right? Sometimes you want to operate at 512 bit granularity. If you modify the DRAM architecture such that you segment the bit lines, which is actually explored in different ways to make DRAM more energy efficient, you can actually use that substrate in a nice way also. Again, I don't have time to go through this paper, but there's a lot more to do in this area for programming, algorithm design, and also a better DRAM architecture to support computation. Because again, I will go back to what I said earlier. Today's memory and storage is designed not for computation. It's designed just for storage. We need to rethink it so that we can actually do computation. Okay, how much time do we have? I also want 10 minutes. Okay, I'm not going to cover the other part that you guys didn't choose. So, so we're almost done. But I will tell you that I'll give you a couple more examples over here. If you want to do more complicated operations, you can actually use memory as a lookup table. This is actually taught in logic design books, right? You can actually do memory-based logic. And we should really go into that. What we teach in digital design, like freshman courses, etc. We should really think about using memory for that purpose also, right? FPGAs do some of this, but DRAM and flash memory and other technologies can do this at scale. I'm not going to go through a lot of these things. So what else can memory do? So we were actually quite interested in, again, abusing the timing parameters to do other functions or to explore other functions. I'm going to give you some examples, and then I'm going to talk about adoption issues, and then I'm going to finish. So in this work, for example, we showed that by violating the timing parameters, activation timing parameter, you read some cells, and some cells always fail. And this failure pattern shows demonstrates a device signature. For each DRAM chip, the failure pattern of which cells fail is different. Essentially, it's a physical unclonable function. Now, that's interesting, but every physical unclonable function can be used for potentially random number generator as well. People have been exploring this. We also show that some cells fail randomly. And if you identify which cells fail randomly when you violate the timing parameter, this could be a very nice true random number generator. And this is actually, again, this is a result from real DRAM chips. And we actually have better mechanisms for that also that I'm not going to talk about. Now, I'll mention one more thing over here. In prior work, that compute DRAM work that I mentioned, for example, it showed that by violating the timing parameters, you can get triple row activation as well. Meaning, what we suggested in simulation is possible in some DRAM chips. So by violating timing parameter, you can actually activate 3 rows, which is fascinating. In this work, more recent work, we actually showed that you could get NOT operation, NAND operation, and NOR operation by violating the timing parameters. I'll keep the suspense here. You should read the paper to know how to do this, but I think this is fascinating. Meaning, this is off-the-shelf DRAM chip. You just have an FPGA memory controller that we designed and violate the timing parameters, and you can actually get the complement of a row. In some cases, very reliably. This is not supposed to be happening, right? Well, I'm sorry. This is not supposed to be how you should be using memory because it's not in the standard. But this is actually consistent with the analog operational characteristics of memory. So this is supposed to be happening, except we have not been doing it because we have been thinking about memory as memory, not logic. Okay, we have multiple works in this area. Okay, this was actually, basically, I think in this work, just a takeaway, we show that you can simultaneously activate up to 48 rows in 2 neighboring subarrays. You can perform NOT operation with up to 32 operands. So don't think about these as a single 2-input NOT, but it could be a 32-input NOT. So it could actually aggregate a lot of data. And we can perform up to 16-input AND, NAND, OR, and NOR operations in real DRAM chips without modifying the DRAM chip itself. Now, I'm not suggesting we should use this as a substrate off the bat. We should really be, this is showing a proof of concept that these DRAM chips are already capable. Can we actually rethink how we design them so that we can actually do more? Okay, I'm not talking about Flash, sorry. Any questions? Otherwise, I'm going to talk about adoption issues a little bit and skip over the near memory processing part. And then we will conclude. Oh. Okay. Somehow I'm lost in my own slide, sorry. Okay, there you go. Any other questions? Yes, please. No, go ahead.
Input do that you give to the single DRAM framework is
Yeah.
the logic synthesized netlist, right?
No lit list. This is just basically how your logic looks.
So how would you like take a application and convert into that format? Would you use a logic synthesis tool to convert that into the gate netlist?
We don't suggest that you convert an entire application, although it's possible to do that. We basically have functions, for example, convolution or matrix multiplication. You could actually express that as a logic, right? Logic unit. People actually build matrix multiplication units, right? So not the entire application. The entire application gets composed by these plus other operations that may be executed on the CPU. Yeah. The MIMDRAM paper actually provides a compiler pass that enables a lot of these. So take a look at that. Okay, so like with any paradigm, adoption is a challenge, of course, right? This is a challenge in processing near memory, which is actually easier. But processing using memory is even more of a challenge because now we need to rethink how we do the computation. There are many challenges over here that we're working on and also the community is working on. I'll just put them out there because there's a lot to do over here. Certainly, how do we build applications, algorithms, and software for different types of processing in memory is important. How do we ease the programming, interface, and compiler support? Like what you mentioned is actually an issue with a lot of compilers. How do we enable system and security support, coherence, synchronization, virtual memory, isolation, communication interfaces? There are a lot of interesting questions. There are papers in this direction also. In this slide deck, I have them, but I'm not going to cover them. Virtual memory particularly is a tough one. I believe coherence is a tough one, but it's easier than virtual memory. But we're having a lot of issues with virtual memory today. Even in processor-centric systems, it's going to become even worse in memory-centric systems. How to design the runtime and compilation systems? Because something that I did not talk about, for example, is data mapping. How do you do the data mapping so that you can do the computation in parallel? Today's data mapping schemes are, like everything else, is processor-centric. We map the data to the DRAM banks, for example, or DRAM subarrays, such that we maximize the processor's benefit. We don't think about doing computation inside the memory, right? So that needs to change. And also designing infrastructures to assess benefits and feasibility. I think more importantly, I think we should really change our mindset. So if you think about how we do computing today, it's ingrained in our minds that everything is processor-centric. We make a lot of decisions implicitly because the data needs to move to the processor, right? All of the design decisions that you look at, most of the design decisions are based on this paradigm. Our education is very processor-centric. So if you really want to enable a bigger paradigm, we will need to change that mindset. Okay, so in the end, we need to revisit the entire stack. Okay, let me conclude, and I'd be happy to take more questions after that. A lot of these other slides are near memory processing that you guys didn't want to discuss, and also real processing in memory prototypes that are near memory processors, essentially. Okay, so I think we want to build fundamentally efficient architectures. And that requires us to think data-centric. We want to build fundamentally high-performance architectures. That requires us to be more data-centric as well. And if you could replace this with fundamentally maybe secure I believe that's also more data-centric today because a lot of security issues are actually due to data movement, et cetera, but I'm not going to put that on the slide yet. So this requires us to think about computing with minimal data movement. So let me conclude. I believe we must design systems to be balanced, high performance, energy efficient, all at the same time. This will lead us to intelligent systems. And I will quickly take a detour on balanced over here. So I teach, for example, the digital design course to freshmen, right? Digital design and computer architecture. One of the principles that I say is you need to have systems that are balanced. And immediately later in that course, I violate that principle. Our systems today are not balanced. I've given you all the evidence over here, right? Basically, we're designing systems such that everything is memory, yet we're still bottlenecked by memory. That's not balance. Maybe we should be doing what we're preaching in digital design courses, for example, or architecture courses. So I think I've talked about data-centric computation, but also we need to be more data-driven and data-aware. We should enable computation capability inside and close to memory, and essentially everywhere where we design computing infrastructure. This can lead to orders of magnitude improvements. I've shown you some examples. Even with near memory processing, actually, you get orders of magnitude improvements because now you do application and memory co-design. This can enable new application and computing platforms. I actually strongly believe this, especially with this processing using memory approach. This also could enable a better understanding of nature. This is fascinating to me because I have partly a psychology background. And when I was studying psychology at the University of Michigan, in these courses, people said, basically, computing was a paradigm to understand humans. And psychologists quite quickly abandoned that because clearly computers don't operate like human brain, for example. But I believe with more memory-centric computing, we're probably getting closer to how human brain operates. And I'm going to leave you with that one soon. I think the future of truly memory-centric computing is bright, but we need to do the hard work, research and design and education across the computing stack. And this is an uphill battle. If you're in industry, and if you're actually making short-term money-making decisions, you should not do this immediately. If you're interested in the next big computing paradigm, I think you should really be doing this. OK, I will leave you with this picture and then acknowledgements in the end. This is probably a computing device. I cannot guarantee it. It's very different from what we build today, I think. I'm not suggesting we should imitate this, but we should really perhaps understand how this works and maybe take advantage of some of the principles that it operates on. I don't think this operates on processor-centric principles based on what we know. And I'm not suggesting I know much about it. And I'm also not suggesting we know enough about this. But there is some integration of computation, communication, and storage that happens over here that we don't quite understand. OK, let me finish this. I'll acknowledge people who funded our research. And most importantly, I'll acknowledge my students who've done all of this work. I just speak about their research and also guide them once in a while to do good work. OK, I'll stop here. Yeah, I should also say that a lot of what I've described is openly available online. You can find it. We'd be happy to help if you're interested in getting into this area. We have a lot of tools that are online. We'll be happy to support. Thank you. I'd be happy to take more questions. Yes.
This is just a general observation. So back in the day, I know SRAM used to be solely off chip, and then they brought it on chip.
Yeah.
And so I think I was like, for me, that's like the first example of like compute near memory because they're bringing things closer together.
Yeah.
Even though, granted, I'm using compute using memory. Granted, I don't know. Do you have like an example of like in-memory computing with SRAM?
With SRAM, absolutely. There are works that have shown in-memory computing with SRAM for sure. So a lot of the principles that I actually described, bit line-based computation, is applicable to SRAM as well. Yeah.
So like, there's like called
embedded DRAM, yes. OK.
Next kind of version.
Yes.
A lot of people are looking at it.
Yeah.
I was just wondering, do you think because I think the first stab I think the industry takes is processing near memory, do you think embedded DRAM essentially is going to be stacked because of this like kind of monolithic stacking?
Yeah. Yeah, so certainly embedded DRAM is easier to integrate with logic. And I think, yes, we should probably be looking into that in the short run, maybe even in the long run as part of the heterogeneous integration of technologies. Yeah. Sure, you're welcome. Any other questions? OK, who wants to go first? You go first.
Widespread
Yeah. So how far are we? I mean, I cannot really say how far we are, but certainly there are companies that are exploring it, and they build chips, like real chips, real prototypes. And with some other interconnect technologies like Compute Express Link, it becomes easier to get adoption. If you actually have a processor and the memory interface as we have it today, DDR interface, it's a lot harder to offload functions. But if you have some flexibility, you can offload functions better. What kind of impact will it have on everyday life if it gets adopted and if applications start using it? Clearly, there's a huge energy reduction that we've demonstrated. Energy reduction can be orders of magnitude lower. Performance can be orders of magnitude higher. But it will take time. Yeah. Yes. Yes. No. Yeah, that's an excellent question, and you're absolutely right. Basically, if you activate multiple rows, reliability issues don't become better. They become potentially worse. And this is something we're investigating and quantifying with the real DRAM chips. But yes, we need to be cognizant of that. And I think there needs to be solutions that enable computation as well as ensure that bit flips don't happen. Yeah, that's also an ongoing area of research. Yes. Yeah. Yeah. I mean, what do you mean by efficiency? Like accesses, like regular accesses, yes. So you don't need to change the latencies. Latencies don't change. Energy of regular operations don't change. You just change the fact that you can actually do computation. Of course, that comes at a cost. You cannot have computation for free, right? Today, thermal issues are not a big problem in DRAM, but if you actually start computing in DRAM, all of those arrays fire up, and you're doing like millions of operations per activate cycle, then you need to have better cooling in DRAM. No question about that. But that's something that we're paying for today, right? If you look at all of these accelerators that people are building, they have substantial cooling for them. If you read the Google TPU papers, they need huge cooling infrastructure. I think this is where the mindset also affects, right? People think of memory as memory. Oh, it should not have cooling. Well, if you think of memory as computation, it's an accelerator, right? Now it should also have cooling. And this is no different from what we're doing today. And hopefully it'll be much more efficient than those accelerators. Yeah, that's a very good question from that perspective. Yeah. Yes. Okay. Yeah, good question. I'll defer to your question. Maybe you can write to JEDEC. JEDEC is the standards committee that determines what gets into the DRAM standard and what doesn't get into the DRAM standard. Unfortunately, there's a lot of non-technical issues that plague that sort of decision-making in the industry. I can get into more details, but even RowHammer, for example, the first paper that we wrote on the topic was 2014. And it was not acted upon as seriously as it should have been. And finally, JEDEC has actually more seriously acted upon it in 2021 after we wrote the next paper showing that all DRAM chips are vulnerable and existing solutions are not good. So it takes a lot of effort because just to give you the perspective, usually there are hundreds of companies associated with JEDEC, and it's very hard for them to agree on one thing. Yeah. Yeah, it's yeah, yeah. When I talk to my students sometimes, especially when their papers get rejected, I say there are multiple things that are against innovation. One is the standards committees in general. The other is the review committees in general. You know that, probably. Yes, yes. I'm sure PhD students here know that. Okay, thank you. Yeah, yeah, thank you. Sure.